All right. So we are back. I am sorry that what do you call it? This video is just a little late this week. I'm teaching 3 5 week online classes and just trying to happen to make all the videos for all of them. So made some other videos because I knew this video was going to take a second. So uh, hopefully you just couldn't do homework on Monday and it didn't matter. But I knew this video was going to take a second, so I needed a good chunk of time to really get this done for you guys. Because this video is really, I would say, that first week we did stuff on limits, which again was good. And you'll see how it's needed as we go through the course, and not just this course, but calculus. But limits are not the main thing in calculus. And I would say that this is the cornerstone of this whole class, Calculus 1. This is the thing. This is really the new thing that we're doing. That again, a little bit like I was talking about in the other lectures, that Leibniz and Newton really invented to be able to do what ends up being modern science, basically, right? Um, so in order to really move things forward for us as humanity. And I say that that's not even overplaying it. Really, for things to move forward in humanity the last 400 years in terms of what we can do technology wise, what we can do in sort of shaping our world, we needed to solve this old problem. That one that actually for thousands of years humanity have been trying to solve. We needed to solve this old problem, and actually, during a pandemic in the 1600s, both Newton and Leibniz were kind of worked on it. And crazy thing actually is that Isaac Newton and this German mathematician Leibniz, they were both working on this old problem. I'll tell you what that old problem is, but they were working on this old problem. And they both separately, they were not corresponding. This was not two mathematicians kind of bouncing off each other. They just were cloistered up in their house. Um, Both independently at the same time figured out this problem. And in figuring out this problem, it gave them the key tool that they need to, that not just that they would need them to as mathematicians, but they were also scientists. I don't know if Leibniz was a scientist, but Newton was also a scientist. Um, but not just that they would need, but that all of, like essentially all of civilization in modern society. When I say modern society, I mean just kind of what we think of that now. What they would need in order to do all the science and innovation that we've done in the last 400 or 500 years. So quite literally, the one thing they discovered, there's actually two things they discovered, and the second thing you'll see in Calculus 2. But the one thing they discovered suddenly made all this scientific analysis and progress and engineering and all this kind of stuff possible. So I can't actually overstate this. The thing that we're going to talk about today, this old problem they solved and how they solved it, is how modern civilization has sort of moved forward, as in terms of technology, in terms of reshaping sort of the world and modern society, etc. Now, that's that side of things. So we have humans have a ton of other moral issues. We just okay, this is college, so it doesn't matter. We just fucking hurt each other is what we do. It's maybe within small groups we figure out how to do it better, but in large groups we just kind of hurt each other a lot. So I am not saying we've necessarily solved that side of things. And we've seen some improvements or got better there. You could argue one way or another, but we definitely haven't solved that side of things. But in terms of science, in terms of technology, in terms of recrafting our world and how we're able to live in it. I literally cannot overstate that what we're going to talk about today is the thing that's made this happen. Taking what they did and taking it forward, and it is the thing that's made it happen. So, what is this thing? This thing is called the derivative. And you'll actually see for the rest of Calculus 1, that is what this class is about. It's about the derivative. But this thing that has moved society forward is called the derivative. But like I said, the derivative, so the derivative is an answer to a very old problem. And I'm not exaggerating when I say literally a problem different societies and cultures and, basically mathematicians from different societies and cultures have been working on. Again, not overstating it, not exaggerating, literally for thousands of years. So let's look at the old problem. That's where we're going to start. Let's look at the old problem and kind of look at why it was a problem, why they couldn't figure it out. And we'll kind of talk about again how Newton and Leibniz kind of solved this problem. So the old problem. What I'll do is let's look at the function of x equals x squared. What I want to do really quick is I want to graph this function. Graph you guys are well familiar with. I'm gonna scale this out. I need to see some spacing here. So let's kind of scale this out. So the old problem. So I'm gonna graph f of x equals x squared for you. There. These points are just skeletons to work through. Skeleton points to work through. Let me see if this is gonna be. Maybe I need to expand this out more. So what I want to do, just so we can really see some, we're going to talk about here well is, actually, so on the x-axis, usually when we do this, we scale the x and the y-axis equally. Let's make the space between the tick marks the same. I'm gonna make it so the x-axis, a lot more space between the marks than there is on the y-axis. Again, it's just visually so we can see what's going on. So think about this like adjusting the horizontal. Well, actually, I was gonna say adjusting the horizontal on the TV, but we don't do it anymore. I forget the term that they use for like, say like when you're working with a video game or some sort of visual audio production app or something like that. I forget the term they have for stretching out the vertical like this. But maybe maybe you know it or remember it. Let's do something like this. So we're just gonna count out to 2. Something like that, and maybe something like that. All right. So then the way this looks is this is gonna be this, and then 2 will go up to 4. This will be like this, and 2 will go up to 4. Not seeing straight, right? Yeah, sure, that's roughly there. All right, good. Let me draw the graph. This is good old parabola that you guys know well. Not just that you guys know well. So when I say this is an old problem, parabola is actually a shape that has existed way before algebra ever existed. It's actually a shape that comes from geometry. It comes from studying geometry. So it comes from, I mean, we have the name from Euclid's geometry, carpenters, surveyors, etc. in Egyptian civilization, Chinese civilization, a bunch of different civilizations all over the earth before the Greek mathematicians kind of came together and codified all this mathematical knowledge and information. They knew about the parabola as well. It was one of a common shape that they used. So this shape, we call it the parabola. This has been around. Cultures and societies have looked at, used, kind of tried to study and figure this shape out for thousands of years. All right, so the old problem. Now this is actually a little bit too stretched out. Seconds. Always the hardest thing actually with this presentation derivative is function show this. That'll have to work for now. All right. So here's the old problem. So the old problem is, first let me remind you, if I want the slope between 2 points, so let's say I'm gonna draw what's called a secant line, so just a straight line between these 2 points. If I want the slope these 2 points, or the line between these 2 points, how do I go about finding that slope? So you might remember from a algebra class, rise over run, something like that. So essentially you would use, I'm gonna mark these two coordinates, this is 1, 1. This is 2, 4. And you would figure out how far horizontally you're going. So basically you would subtract your x values and you subtract your y values to figure out how vertically you're going. And your slope would be delta y over delta x. So in this case, it would be 3 over 1. So my slope here is 3. Easy enough. So this not only goes back to algebra, but again, just goes back to geometry. In geometry, when you're looking at the slope of a line, that's what you do, is you look at 2 points and you're finding sort of the geometrical equivalent of delta y over delta x. So part of what I'm trying to say though is it makes sense with 2 points, because what I need to find the slope of a line is I need to figure out what is my vertical change. So this is why I like to think of that as rise over run. I need to figure out so slope is just a ratio of vertical change in a line to the horizontal change. So rise over run. And we're just basically, so I tell my algebra classes always that that's really what slope is about. It's sort of a way to measure how vertical a line is, essentially. So you take a ratio, you take a comparison of the vertical to the horizontal, delta y over delta x, rise over run. And so it makes sense with 2 points, because then I can actually measure that, right? I can figure out how far have I gone up to get from one point to another, how far have I gone over. Now, like I said, the old problem, so for a secant line, they call a secant line, but just a line through 2 points like this that we know, easy peasy. It makes sense. That's what slope is. What about, so the old question that they had for a while, what if instead of the line through those 2 points, what if I wanted to know the slope of the line that goes just through 0.11 and then skips right off? And we call that the tangent line. And again, these terms actually come from geometry. So we call this the tangent line. The tangent line is the line that just hits a point on a curve, goes right off of it, and it goes right through it. So what if I wanted the slope of that line? The slope of a line is still always the same, delta y over delta x, rise over run. But for the tangent line, the question is, how do I judge how far it's gone up and how far it's gone over? How do I judge rise over run? What do you guys think? So hopefully you're kind of stuck on it, because that is the problem. Actually, this is the old problem. If I draw the line that goes right, just grazes right through the point on not just x squared, but any curve, Problem is that line goes through one point, but we don't have a second identified point, right? And maybe we could make some measurements and figure out that point at some other point there. But I will also, another note is that any other point that I would use on this tangent line is not on the curve. So the curve is nice because the equation for the curve, the function defines all the points on the curve. But this space out here, this is what do you call it? These are the badlands, these are the wildlands, right? These are not controlled. I don't have a function. I don't have a definition of those points outside of that line. Again, so you could go and try to measure it and do stuff like that. But in terms of this function, the function doesn't tell me anything about these points outside of this line. This is my wildlife area. This is my wild space. I don't know any of those points. And so the old problem they had for thousands of years is if I draw a tangent line definitely has a slope, but the points that it goes through, so anyways, yeah, it only goes through one point on that curve. So I can't use the curve to tell me the slope of that line. I don't know what the slope of that line is. So like I said, this was a problem for thousands of years, both for Greek mathematicians, but also again for surveyors, architects, um, carpenters, etc. In both the Greek civilization, Chinese, Hindi civilization, whatever, like all these old civilizations before that, just as a matter of necessity. So you think of it as a carpenter, as an architect, as a farmer surveying your field may need to know, so this is an idea that you need for something that you're building. The slope of this line tangent to the curve. And for thousands of years, they tried to figure this out and they couldn't. They had no way to accurately get slope. Um, So along comes Newton and Leibniz. And by the way, I will say that I think the idea they started with wasn't like they just came up with nugget of the idea on their own. So the idea they started with probably was it was a limiting idea or a kind of idea involving limits that the Greeks had tried. They just didn't have the mathematics to kind of do what they were trying to do, right? Um, so I think Newton and Leibniz started there. But I will say beyond that, I mean, they really did they invented the method for this. So literally, I was telling my Cal 2 class sort of the same thing. I mean, the thing you have to realize about calculus is calculus was invented to solve two old problems. This old problem, slope of a tangent line, and then you'll see in calculus 2, the area under a curve. So again, I keep saying these are old problems, but it's just interesting looking at humanity and culture and history and the things that, there's everybody, becomes a carpenter, right? Every society has carpenters and they have architects. And so they end up coming across the same problems and they try to solve them. So even if they're not trading partners, they're not exchanging ideas and stuff like that, everybody kind of comes at these same issues that they need to solve. And so everybody has kind of has come around, had to kind of struggled with two problems as terms of geometry, whatever that society called geometry. So we study geometry, like Euclid kind of put it together, codified it, showed that it all worked with each other. But Euclid was taking a lot of ideas that had been independently kind of figured out or shown, or we kind of hypothesized that they worked from a bunch of different cultures and times. All of the geometry that Euclid was looking at, those geometry that these other cultures had looked at. And so the interesting thing is that geometry, whether it was Euclid's or it's all these old farmers and architects figuring things out, geometry always tell you a ton of things about objects with straight sides. And it can tell you a ton of things about circles. But once you get beyond straight sides and circles, once you get other kinds of curves, it's really geometry kind of falters there. So sometimes it has formulas for those things, but most of the times it doesn't. So again, the old problem is all these architects and carpenters and engineers, etc., would inevitably we need to use shapes that weren't nice straight-sided shapes, and they weren't just a simple circle or an ellipse or something like that. And so what they inevitably ran into was they couldn't figure out, again, so two old problems. They couldn't figure out slope tangent line. They basically couldn't figure out the slope of at a certain point on the curve, and they couldn't figure out the area under that curve. So as Newton, basically in Newton and Leibniz time, as they're starting to study physics and stuff like that, they're realizing that in order to do physics and all of this sort of new science that they saw that it was there, but in order to do it, algebra wasn't enough. They needed more mathematics. So I mean, again, so I always talk about this in this lecture, and I know this this is me. Not only this is not just not being excited, but I really want you to think like, imagine being back in this time, kind of what happened, where everybody is seeing this science and these possibilities and these things that could work and how technology and things could move, but literally trying to do the work and realizing that the mathematics that you have just doesn't do the thing. And then two guys literally sit inside during a pandemic for 2 years. And when I say they invented the mathematics, they literally invented the mathematics to do the physics, chemistry, this science that was coming up. They literally just sat down and were like, well, shit, I got to figure out how to do this. I got to figure out new mathematics to make this work. Again, I want you to, do you realize how crazy that is? How crazy that is. You sit down and be like, everything that's come before me is kind of led up to this, and I'm going to use that information, but everything that's come before me doesn't work, and I need to invent the new thing that makes the new stuff work, right? That is freaking crazy. Like, and honestly, that is every mathematician's and scientist, I would say every mathematician's and scientist's dream. How freaking cool would that be for you to sit down and invent the new thing needed to do the new stuff? You look back in history, so this is not the first time sort of this has happened. It's actually happened a decent number of times throughout history where there was some major idea or concept that ended up moving a lot of societies forward, but everything before that has sort of worked up to it, but it wasn't enough to do it, right? So they needed a new idea, a new concept. And the interesting thing is that not always, but it often happens in twos. There's often two people sort of figure it out at the same time. It's really, really weird. So that's, I mean, really, like if you look back in history on a couple things, some major ideas and concepts that have moved societies forward, and it's often two people. But again, the crazy thing is what they do is they don't make it's like they don't tweak old things. They just freaking come up with new stuff. Oh my goodness, like how how fucking incredible is that? Like how fucking awesome is that? Like that, again, not everybody gets to do that, but that you could be that person, right? You could be that person to like come up with the new idea and invents the new thing. Um, so I just think it's amazing. Really, really cool. But I'll also sort of bring that up to, like, again, as we're doing the math, I want to teach you the math, but I also like there's some of these things, there's moments in history and concepts and philosophy and stuff like that that are so momentous that it's like you shouldn't just do the mathematics. You should sit back and really look at this and like just kind of bask in what's going on, sort of realize what's going on. So again, when what we're about to do, when I say that they invented the mathematics to do this, that is quite literally what happened. Again, resting on stuff that had come before, but the stuff that had come before wasn't working. It wasn't enough. They just invented the mathematics to make this happen. Okay, so so cool. Um, sorry. So we need a way. They needed a way to find slope of this tangent line. And again, the problem here is there is not a second point out here. There's no defined point out here that I can use to figure out delta y over delta x. So Newton and Leibniz are sitting inside their houses during this pandemic. And this is the idea they come up with. So I just erased that secant line, right? So I want to redraw it in so that we had this secant line here. Now, the first question, is the secant line the tangent line? Obviously not. But notice that, so the secant line is not the tangent line, but at least the slope visually is kind of close to what it would be for the tangent line. So it's not the tangent line. But the slope of this line, the secant line, is, like we said, equal to 3. And so we could use that as sort of a first guess at the slope of the tangent line. And when I say guess, what I'm saying is we're just saying it's close. Now, it's obviously not the same, but it's close. So then Newton and Leibniz idea was, well, again, the problem is I don't have a second point, and you'll kind of see what they did is essentially it's not like they invented a way to have a second point on this tangent line. So they didn't resolve that. But what they said was, okay, that's the secant line from, so if 1, 1 is the point the tangent line's through, it's the secant line from that 1 to the point with an x value of 2. So the next question, or the next thought is, what happens if instead of the point 24, I choose the point, basically I cut my x value down from 2, maybe 1.5. So now I want to draw the secant line through 1, 1 and this point at 1.5. And again, I want to ask the same question. Is that secant line the same as the tangent line? But no. Second question, different question. Is the slope of that secant line closer to the slope of the tangent line compared to the slope of this previous secant line? Good, yes. So visually we can kind of confirm that. So if I choose an x value for a point closer to 1, 1, the slope of that secant line is by definition kind of automatically closer to the slope of the tangent line. So maybe, so again, okay, so the slope was 3 the first time, so maybe the slope is, and I can actually get accurate on this. So give me a second. So 1.5, 3/2 makes 9/4. So the slope this time is going to be 5/4 divided by. So what I'm doing here is so this point, if you plug in 1.5 or 3/2 to this, that point is, we'll do it, it's 1.5, comma 2 1/4. And so now when I do my subtraction to get my vertical and my horizontal, my delta y and my delta x, the delta y is 2 1/4 minus 1, which is 1 1/4. Delta x, or the horizontal, is 1.5 minus 1, which is 1/2. So the first time my slope was 3. Second time, it's going to be 1 1/4 divided by 1/2. 5/4. I'm going to write that as 5/4. 5/4 divided by 1/2. You take 5/4 and divide it by 1/2. You actually get 2.5. Now my slope is, so my slope on the second secant line is 2.5. Now again, they kind of looked at this, so they're experimenting, right? So they chose, let me make my x value closer to 1. And they got now a again, the slope of the secant line is now different, but like you guys, so you guys said it looked closer. Now you can actually calculate it to see that it's closer to whatever the slope is for this tangent line. So then the thought is, well, I could keep doing that, right? So to make a slope, I need 2 points. So the derivative doesn't resolve that issue. You need 2 points to make a slope. But Newton and Leibniz idea was, well, what if I just keep making this point closer and closer to the 1, 1? Then the limit of these slopes as my point gets closer and closer to 1, 1, what should the limit of those slopes be? The limit of those slopes should be the slope of the tangent line. Or another way to think about it is those secant lines, as you make the x value closer and closer to 1, that literally that secant line is going to tilt and get closer and closer to being exactly the tangent line. So another way to think about it is the limit of those secant lines is the tangent line. And so, like I was saying at the beginning of the lecture, you need the idea of limits, because limits is actually what makes this happen. You need 2 points to make a slope, so we never resolve the issue if the tangent line only has 1 point. So what we do instead is we figure out the slope for secant lines that are closer and closer to the tangent line. And the limiting process, the idea of a limit, tells us then that the limit of the slopes, limit of the secant lines is the tangent line. So the limit of the slopes of the secant lines should be the limit of the slope of the tangent line. So let me just kind of keep drawing this out. So so we saw that second secant line. So then we can make this even closer. We could make this, choose the x value to be 1 1/4. So this diagram is going to get murky. But we could choose the x value to be 1 1/4. And then if you look at the secant line through those 2 points, that is a lot closer to that tangent line. So physically, the secant line has tilted inwards, kind of down, and now is a lot closer to the tangent line. And so that should be for the slope as well. This secant line is tilted down compared to even the last one. Slope of that secant line should be closer to the slope of the tangent. This point is, so I said that I was going to plug in 1 1/4, which is 5/4. That point is 1 1/4. 5/4 when you square it is 25/16. That is 1/9/16. So this time when I do delta y over delta x, so if I'm looking at the slope of the secant line between these 2 points, my delta x on horizontal here is going to be 1 1/4 minus 1, which is 1/4. And my delta y vertical is going to be 1 9/16 minus 1. It's 9/16. Then if you divide this, you flip the 1/4. 4 cancels with the 16 and leaves you 9/4. So you end up with 2 1/4. The slope of the new secant line between 1 1 and 1 1/4, 1 9/16 is now 2 1/4. Again, we can see visually that secant line physically is closer to the tangent line. It's becoming like the tangent line. So again, the idea is I could keep doing this. I could plug in 1 1/8 and then 1 1/16. I could plug in 1.1, 1.05. And for each one of those, I'll get a y value. And then when you do delta y over delta x, these values are going to get closer and closer to the real value of the slope of that tangent line. So what Newton and Leibniz figured out is if you could take the limit of this process, then we've got it. We've actually got the slope of the tangent line, because the limit of the secant lines is the tangent line. So if I can take the limit of this process, of the slope values that I'm getting, then I can figure out the slope of that tangent line. Right. And like I said, this was huge. This quite literally changed, modern scientific study. This, by the way, is honestly I would say is the difference between modern scientific study and older scientific study. So we kind of have this idea that we have this feeling that we invented science and we didn't. So the Romans did science, the Greeks did science, Chinese civilizations did science, etc. Um, they actually really intellectually pushed and studied, I would say, a lot of the ideas that we've like modern scientific thought has gone through. The problem is they didn't have the tools to completely get there. So again, without exaggeration, I can tell you that the derivative and then the integral that you're going to study in Cal 2, that has been the difference. Those are the tools that has got us there. Um, so we have been able to do some things scientifically that older civilizations have studied, not have that they studied but couldn't do, not because we're smarter, but because people like Newton and Leibniz invented a tool that the ancients just didn't figure out. Again, they were smart. They really actually labored at this for thousands of years. They just didn't figure it out. We were lucky that Newton and Leibniz figured it out. Um, so that's kind of the idea that gets us there. So a couple things to really emphasize out of it. So the derivative is the slope of the tangent line. That's the idea. So we are going to find derivatives of this function and a bunch of other functions, but when we're finding those derivatives represent slopes of tangent lines. That's what we're really looking at. So there's sort of a couple veins I want to go off with from here. The first thing is I want to show you how we would calculate the derivative kind of out of this idea. That's the slope of a tangent line. And I want to show you that limiting process that we're talking about. So I want to show you how this works, like from the ground up on maybe one or two functions. But then from there, so once we know kind of how it works, you'll see that the process is kind of cumbersome. And so we're going to want not just even just shortcuts, we're going to want some patterns. And so we have the luck of Newton and Leibniz. Like I said, not only did they figure this out, they then kind of played this forward and figured out patterns for this thing called a derivative. And since then, other mathematicians and scientists and engineers have kind of carried that work forward and really solidified a lot of those patterns. So the advantage that you guys have is probably literally a couple hundred years of work and study on derivatives. I'm going to present to you guys in essentially 3 chapters, roughly for 2 chapters. So we're going to get to condense a lot of this. Now, I don't want that to scare you on like, oh crap, I'm going to be learning a lot of high level stuff and it's going to be too quick. What I'm saying, I'm not saying, actually, you really don't have to worry about that. I'm not saying that's going to happen. What I am saying is we have the advantage of people took a while to study these things amongst all this other stuff going on in life and civilization. And we can condense it into 2 or 3 chapters where I can show you what the derivative is, why it works. And then I can say, now let's study the patterns that we figured out from it. So you're not going to have to create the pattern. We just get to study it and then we get to use it. So we are going to by condensing it, we're not going to make it harder. It's just, you don't have to do the hard lifting work. Actually, it actually makes it easier. You don't have to do the hard lifting work of figuring out what the patterns are and why they work. I just get to tell you what the patterns are. And so as long as you trust that these patterns are what they are, so I'm not going to go through proving them, especially for a 5-week class. As long as you can trust that the patterns are what they are, then you will know then. So again, like I said, we'll do a hard lift on a couple derivatives so you see why it works and how it works. And then for the rest of not just this week, but basically the rest of this course, I'm going to show you the patterns. And as long as you can trust that the patterns work, you then can do the derivatives and use the derivatives to figure out things that literally took people time-wise a couple hundred years to really solidify. So you're going to get the easier end of it. You just have to trust the patterns and use the patterns. So yeah, so going back to that's sort of so our lecture today, we want to do a couple examples of actually how to calculate the derivative and do the hard lift. And then I will start into a couple of the simple patterns we have with derivatives for basic type of functions. And it'll be your job to kind of like connect with those patterns, but also trust those patterns. So memorize them, but even better than memorize them, what I'm saying is trust them. So I'll give you ways to kind of visualize those derivatives. Anyways, so let's actually start with this function we're talking about. So again, we know there's a slope to the tangent. We can see, you can even see in the numbers here, like these slopes that we got for the first three secants so far, this is going somewhere. If I keep calculating this, I'm going to get a sequence of numbers that has a limit. So let's see if we can figure out a way to find that limit exactly. So let's figure out how I want to present this. We're going to find the derivative for a function for f of x equals x squared. So first time we're going to do this again, we're just going to do this. We're going to figure out how they actually calculated. Sorry guys, I keep repeating the same stuff. How we actually calculate the limit of the slopes here, how we actually calculate the derivative. I want to go back to the derivative is the slope of a tangent line. And slope is delta y over delta x. What I'm going to do here is I'm going to write this delta y and delta x, but instead of numbers, I'm going to write it what we call symbolically. I'm going to write it using this function. So every time I calculate, so going back to this picture, every time you calculate this slope, what you have is you have one point on the curve and another point. And you're using the y values for those points and you're subtracting them. So you're taking, say, so let's go back to the initial secant line that I gave you guys. Between 1, 1 and 2, 4. Let's say that we didn't know these coordinates. So say we didn't know these coordinates, but I want to calculate the secant line between this point and this point. I would have to figure out the difference in the y values and the difference in the x values. The difference in the y values is delta y, the difference in the x values is delta x. So if I didn't know the numbers, if I wanted to label these points just in general, if I don't know those numbers, I can call the first number x1 and I can call the x value for the first point x1 and the x value for the second point x2. Just basically saying first x point and second x point. So they use those subscripts. It literally is just saying first, second, third, fourth, fifth. It's our way mathematically to say a list of things. But whatever these points are, whatever the actual numbers are, then let's go to the first point, x1. How would you write the y value here? I guess this is not a trick question, but I guess I just want you to remember something simple from algebra, but you may not be thinking about right now. So how would I label the y value here? So what we know from algebra is f of x is our kind of stand-in way of saying y, right? So when I say f of x, what I really mean is plug in x, this equation, and whatever I get out of it is my y. So f of x literally in notation is my stand-in for y. So the y value here on the first point would be f of x1. Y value on the second point would be f of x2. Again, I think that this looks weird, but just know that we're just trying to say the first y value or the y value that comes from x1 is f of x1. This is the y value that comes from x2. So if I want delta y, if I want the difference in the y values, or basically how far up do I have to go, all I got to do is take f of x2 and subtract f of x1. And give me a second. Let me do a little bit of relabeling here, guys. Sorry. So I'm going to call this first point, I'm going to call it f of x and f of x. Right now we can keep the x2 and f of x2. Basically, don't worry about y because it's more about the way this notation reads when we finish this process. So, but my difference in y values will be f of x2 minus f of x. So delta y, no matter what my function is here, is going to be f of x2 minus f of x. And what would my delta x be? So what would the difference, the horizontal values, or how far would you have to go horizontally to get from here over to here? But again, without the numbers, you can't subtract and give me a nice clean number, but you could say it's x2 minus x. Because that's, again, if you had the numbers, when we had the numbers here, when this was 1 and this is 2, that's what you did. You just did 2 minus 1. So delta x always is x2 minus x. And we started out with this point up here, and then what we did is we moved this point in. Move the x value closer. Move the x2 closer to x. Moved it to here. We moved it to here, and we could have moved it farther and farther in. So what I was saying by the end is if you took the limit as you moved this x2 farther and farther in, then the limit of the secant line should be the tangent line, and therefore the limit of this slope should be the slope of the tangent line. So it ends up then the derivative. Well, so the derivative is a slope. There's a couple different ways they're gonna start to mark this derivative. One of them is that they do f and they have this little tick mark. So the way we say that is f prime, and prime notes the first derivative, the derivative. So derivative is slope, but this is my symbol that I'm going to use for it when I'm trying to say the derivative. But what we just said is if we take the limit as the second x value gets closer and closer to the first, so as x2 approaches x, then this will tell me the slope of the tangent line. Therefore, it tells me the derivative. So this is actually not like, so symbology wise, this has a few different symbols from the way that you see it written in the book if you are following along, like reading the textbook. So so this symbology wise looks slightly different than the way they wrote it in the textbook, but it says and means the same thing. So this is delta y or delta x. And if I take the limit as the second point approaches the first one, whatever my first one is, then this slope of a secant line becomes the slope of the tangent line, and therefore it's the derivative. All right. Second. So now let's do kind of, like I said, let's do the work. Let's do the algebra work. And the surprising thing is it is algebra, but the algebra work that Newton and Leibniz figured out. So we need to take the limit as x2 approaches x, this expression right here. And so what we're going to start to do is we're going to take what we know about f of x and kind of plug it in here. So f of x2 is gonna be whatever I get when I plug x2 into this. So f of x2 is gonna be x2 squared minus f of x, which is x squared. Then x2 minus x, I can't do anything different with that. So now what we're gonna do, or what we have to do, and we want to find the limits this as x2 approaches x. So we saw a little bit of this in the last chapter, but what we have to do here is, so notice we have a fraction. Want to find the limits of this fraction. The problem here is, so the first thing to note is the problem corresponds to the old problem, but the problem is that if I plug in, so when we found those limits in the last chapter, we essentially just would plug in. In this case, it's telling you to plug in x2 for x. The problem with that is if I plug in x2 for x, I get 0 on the bottom. And I get it on the top. I'm gonna get x2 squared minus x2 squared, which is a 0. I'm gonna get x2 minus x2, which is a 0. And 0 over 0 is indeterminate. It doesn't tell me anything. So in the last chapter, we saw examples like this. So we saw some examples where you plugged it in and it just gave you a value, right? But we saw some examples where when you plugged it in, it gave you, in particular, gave you 0 on the bottom, which was a problem. So we needed to do some algebra to kind of massage this into a place where we could plug in x2 for x, and it would give us what do I call it? It would give us a result. I'm sorry, guys. So when I was describing this, it actually should be the opposite. You should be plugging in x for x2. So as x2 approaches x. So actually, same problem, but just different symbols. So if you plug in x for x2, you get x squared minus x squared, which is 0, and x minus x on the bottom, which is 0. And again, there's no calculation there. So we need to algebraically manipulate this to a place where if we do plug in x for x2, then we get something out of this. So what do you see can be done with this algebraic? In some sense, this is asking you to practice some of those skills you picked up in the last chapter. And I'll actually give you guys, so what we'll do here is I'll have you guys pause on your side and I'll pause on my side. Now I actually want you to take a second to work on this. See if you can figure out algebraically how to simplify this so you can plug it in and you don't get zeros, especially on the bottom. And if you can't, that's fine, but take a second and see if you can work it. All right. Let's see what you guys are getting here. Or again, maybe if you couldn't figure it out, that's fine. So let's jog our memories on some things that worked last week. And then I will say too, you didn't figure something out. It also is possibly just because of this x2 that you're seeing. We're used to seeing plain letters as variables, y, x, z, w. So literally, visually, psychologically, you're comfortable manipulating those, working, doing our algebraic manipulation with those. We're not as comfortable when you have something like this. So what I'm about to do, once you see it, you may be like, again, if you didn't get this, may see this and be like, oh, I should have seen that, or that makes sense, or why didn't I see that? And it's honestly likely just more because of the subscript there. So what I see in the top though is we have one thing squared minus another thing squared. I can factor that into x2 minus x times x2 plus x. And let me still I still need to include the limit here, so let me write all that in. So it's the limit x2 approaches x. But we're gonna end up with x2 minus x times x2 plus x on top. And we still have the x2 minus x on top, but again, like we saw last week, a lot of times you try to do, if you, there's something can be factored, you factor them out because then you might have common factors that cancel. And notice we do here, the x2 minus x's cancel. And x2 minus x is what was giving you 0 because x minus x is 0. So notice, just like we saw last week, we're canceling out thing that is kind of causing the issue calculation wise. So what this leaves us with is we could calculate the limit as x2 approaches x2, now it's just x2 plus x. Now this works, so x2, I'm going to replace it with x. What is x plus x? That's 2x. So what that tells me, so kind of, let me summarize this all. So f prime, so the derivative of x squared is the function 2x. Again, the derivative is the slope. So this function actually tells me the slope of the tangent lines on the x squared graph on the parabola for every single x value that I could ask for. So at every single x value, all I have to do is do 2 times that x value, and that tells me the exact slope of those tangent lines. So they ask you to find the derivative, you've got it. They also, so again, like I said, this is the derivative. This tells me slopes of the tangent line. So they could also ask you something like this. What is the slope of the tangent line at at x equals 1. So let's kind of literally finish off the beginning question. We were trying to find the slope of the tangent line specifically at 1, 1, or when x is 1. Or f of x equals x squared. So what's the slope of the tangent line? Well, the derivative you just figured out was x squared, or sorry, it was 2x. Oh my goodness. The derivative is 2x. So then if you want the slope of the tangent line, you just plug in your x value. So the slope at 1, or the derivative at 1, is 2 times 1, which is equal to 2. And there you go. So the slope of the tangent line on the x squared curve, 1, 1, 2. And notice, going back to the little demonstration I was doing, let me write these numbers back in here. Notice the slopes that we were getting. We started, first secant line had a slope of 3. That was 2.5, 2.25. You can actually see it getting closer and closer to 2 as we kept calculating those slopes of the secant lines. So again, the limits of the secant lines is the tangent line. So the limits of the secant slopes is the tangent slope. That's what we call the derivative. So in general, no matter what function you're given, you can actually run this process. So you can write this same, what do you call it? Sorry. I'm getting some vocabulary right now, being tired. But you can write the same expression here, f of x2 minus f of x over x2 minus x. The limit as x2 approaches x of that. No matter what function I give you, you can start working this out using what the function is. And this process algebraically will give you the derivative every time. The derivative tells you the slope of the tangent lines. So this is how we take a derivative actually. So this part here, this is really how we take a derivative, and this is what Newton and Leibniz figured out. And so like I said, they suddenly figured out, they kind of invented the mathematics, but really figured out the mathematics to this long-standing problem of finding the slope of a tangent line. Now, like I said, we can do this every time. So one version of this class is I give you all these functions and I ask you to take the derivative and you run this every single time. And you can see that this wasn't so bad, but nonetheless, this involved a decent bit of algebra. And also you definitely had to, you can imagine if you have other functions that you're plugging in here. Here we just had to do some factoring. You would run into a bunch of other algebra, weirder algebra that again, you know and you've seen, but maybe you haven't mastered yet, or just you don't do often. So again, one version of this class, I could just give you a bunch of functions and say, find the derivatives of them. And you just, every time you just do the hard calculation, work out all your algebra, and you get the derivative. Uh, However, that would take us a ton of time, right? So like I was saying earlier in the lecture, from here, I'm going to give you guys the advantage of now that you know how to do a derivative, like for real, let's figure out the patterns that they found for these derivatives. So basically what's happened is instead of just finding the derivative for every function every time this way, they've looked at different types of functions and figured out patterns for the derivative of those functions. And so we're going to learn those patterns, which will allow us to take these derivatives a lot quicker. So let's talk about maybe the first pattern we want to learn. He's like, I'm gonna pause this. I need to get some water. All right. So let me show you some of the patterns for derivatives. So like I said, for this lecture, so from here, we'll focus on some of the patterns with derivatives and then we'll just kind of use them. So we're going to take some derivatives again, and we're going to find some slopes of tangents line again, but this time we're not going to go through this calculation as much as we love it. We all know we love it, but we're not going to go through this calculation again. We're going to use these patterns that I'm going to show you. So, derivatives. I think the way I want to do this, I'll kind of want to, it's a big table slash visual object going for you guys to show you some of these patterns. Mm. Well, the first pattern I really want to talk about, you'll see that most of these patterns correspond to types of functions. So like I said, what they did pretty immediately is they looked at types of functions, they mathematically proved some sort of pattern for how you take the derivatives. So again, we could do this every time, but this is going to get horribly tedious and just a lot of strange and weird algebra that, yes, technically we could do, but why do that when there's a pattern to it, right? So by the way, that's often what mathematicians do. So I'm a mathematician, I'm published. I try to find patterns. I try to find simpler patterns or larger patterns in complex details of stuff like this so that we can use the patterns. The patterns are the truth. We can use the patterns instead of always having to go through some algebra, some calculation. So power functions. Remember that power functions is something like x raised to a power. And so pattern that we figured out there, Sorry, I'm just trying to decide a bunch of different things here, but so the pattern that we figured out there. So if I want to take the derivative, so I'm going to show the derivative now this way. So instead of writing f prime, I'm just basically saying this is my function and I'm doing the derivative of it. But pattern that we figured out here. What you do is ends up that every single time you take the derivative of the power function, whatever that original power is, ends up coming down as a coefficient. It ends up being a coefficient in front of x. And and the result, and then the power that you're left over with is one less than your original power. So for instance, let's go back to this x squared. So x squared, so I was a bit intentional here. Not just a bit intentional, very intentional. So x squared is a power function. It's x to a power. Notice if you fast forward to the end, the derivative was that 2 ends up being the coefficient in front of x. And then the power on x is actually a 1, which is less than 2, minus 1. So it ends up not just with 2, but any power you could put up there. And that, by the way, includes not just integers. So we'll kind of see, we'll see some examples where you could have a fraction up here, you could have a negative number up here, you could have a decimal up here, it doesn't matter. That number always comes down and gets multiplied as a coefficient. Then the power drops 1. So that's the way I actually think about it, is the power drops 1. I actually think about it like a ladder. So x squared starts at the second level, the power drops 1, so I'm going to be x to the first power. Then that power drops down in front as a coefficient. It gets multiplied as a coefficient. So this may, I'm trying to think of a good way to write this that isn't so formal, but this may be a good way for you to remember it. Think what I'll do actually. So let's still, I don't know. I don't think that's going to help us either. I've been trying to figure out. I often actually try to figure out different ways to write things that are not so formal. I will say one of the things that I don't like about textbooks. So I'm a mathematician. I see things theoretically, but I realize for a lot of people that the way it's written theoretically actually hinders you. It's like the language isn't clear and it hinders you from seeing the pattern. So that's one of the things I do then as a teacher. I leave my mathematician behind and I try to find a better way to write it so you can see kind of the pattern clearly without being kind of encumbered by some weird theoretical way that we like to write it. Anyways, so oh yeah, I think that's, still don't like the way this is written, but that's probably the best we can get for today at least. So derivative of power function, multiply by the power as a coefficient, and you drop the power 1. So let's do some examples of that. So this is where I want to start to bring in some problems from the book, or just we're going to do some exercise out of the book. So by the way, everything that I'm teaching covers not just 3.1 but 3.2. So this will cover 2 sections for you guys. Oh, actually, so let me create some of my own problems on this because so let's find the derivative. Actually, Should be writing it a couple different ways. So find the derivative. Let's do something like, let's say f of x now is, okay, so let's make it something like, well, x to the fourth power. Kind of easy enough. So we want to find the derivative of this. So f prime then, again, what I'm going to do is I'm going to drop this power in front. I'm going to, I'm going to multiply by the power in front, and I'm going to drop the power 1. So this is going to be 4x cubed. And you got it. That's your derivative. Now, again, you could use the definition of a derivative that I showed you on the last part, sort of that rational expression. Oh, difference quotient. So they call it formally in calculus, they call that expression that I gave you guys the difference quotient. So you know. You could do all that, or you could just use this pattern. 4 drops in front, power goes down 1. And like I said, this works even if your power isn't a nice clean whole number. So for instance, now let's find the derivative of the square root of x. This doesn't look like x to a power. But in fact it is. So if you remember from college algebra, square root as a power, what power is that? That's 1/2. This is actually x to the 1/2. Let me write it out this way. So then my derivative, I'm going to drop this down as a coefficient, and I'm going to subtract 1 from this. I'm going to drop that power down 1. So it's going to be 1/2 x, and what is my power going to be? Okay, good. Hopefully you see that 1/2 minus 1, if you think about it like on a ruler, like a number line, you're at 1/2 and you subtract 1, that'll put you on the other side of 0 at -1/2. So this will be x to the -1/2 power. And that is correct. Now, I do want to talk really quick about, dealing with a negative power there. So I do know for Canvas assignments, you can, unless the problem says otherwise, so read the instructions on how they want you to give the answers, but unless it says otherwise, you can write a negative as a power, and not just for the sake of Canvas and your homework, but in truth, mathematically, yeah, negative power is perfectly fine. That's the number. It works. But there is some other ways we can write this, and I want to walk through the other ways we can write this, because then on future problems, that'll help us recognize kind of what we see and then work the problem from there. So again, I want you to go back to your college algebra stuff. So I have a negative power here, but when I have a negative power, what does that really mean? Remember that a negative power means it is x to that power, but on the bottom of the fraction. So this could be really be written as 1/2, and then on the bottom, so with the 2, we would now have x to the 1/2 power. Could also write it this way. Then, like we just talked about, that 1/2 power, what does that mean? That means square root. So another form of this, kind of the final form, like a Pokemon or something. Sorry. But final form is 1/2 square roots of x. So the derivative of square root of x is 1/2 square roots of x. But you could write it either of these other ways. But again, my point in doing these is, again, I want you to recall those connections. That square root means 1/2 power, and that negative powers mean you really have that element on the bottom side of a fraction. So this means we also could take this derivative of something like, let's say now that f of x is 1/x squared. Again, we do sort of see a power function there, but it's on the bottom of a fraction, so this is really a rational function. But it is just a power function in disguise. So if I have 1 over x squared, if I have x squared on the bottom of the fraction, then how could we rewrite this as a power? It's just a straight power. Good, so just like we just saw, negative power means it's on the bottom of the fraction. So we could rewrite this as x to the negative 2 power. Then you could do your derivative from there. You could use your pattern for power functions. And let me see if you guys can do that. So I'll go ahead and pause on your side. I'll pause on my side. Work the derivative of this, and then we'll talk about again just different ways you can rewrite it from there. But just see if you can get the derivative. All right, let's see what you guys got. So the negative 2 comes down, gets multiplied. And then the power goes from negative 2, you're going to subtract 1, so that's actually going to be a negative 3. To be consistent about, I guess, about the way I'm writing this. So f prime is going to be negative 2, x to the negative 3. Good. And that's perfectly good. We can write it that way. We wanted to rewrite it basically without the negative as the next negative exponent. We could also write that as negative 2 over x cubed. Put negative in front of the fraction, sure. And that would be the derivative of x to the negative 2. I'll turn back to that later. Okay, good. So this pattern on power functions is actually surprisingly useful because you can use it on power functions, but you can use it on other things that we, as a normal course, can rewrite as power functions, or at least rewrite as power functions. So you can do rational functions. Sorry, not rational functions, radical functions. You can do rational functions, simple rational functions. All right. Let's see. I want to do 2 more examples to actually get us to see. So I want to do 2 more examples because they'll show us another pattern. So basically they'll show us another, I'll just say some truth, or some derivatives. It's just some patterns with derivatives. But the surprising thing is, again, they use the pattern for power functions. You will find as we go on this course, the pattern for power functions with derivatives just gets used a ton. It is an incredibly useful pattern. So let's look at 2 other problems. I want to look at make f of x this time 5 times x. We still need to do one thing before this. Give me a second. I want to introduce this part. All right, well, let's talk about another pattern first, and we can talk about this. Another pattern, I want to look at what happens with constants when you take a derivative. Well, actually, let's be more specific. That's what happens with coefficients. Coefficients are a type of constant, but they're constants that are multiplied usually by a variable or by an expression. So let's look at what happens with coefficients. Do I want to do an example first? Yes, second, guys. Let me figure out how I want to write this and show this. I still feel like I don't have the best way to, what I imagine in my head is the best way to show this, but for coefficients. So let's say we have some function. So what I'm gonna do here is, um, we have we multiply it by a coefficient. So you have some base function like an x squared or whatever, but you multiply it by a coefficient. So in this case, instead of using a letter like they usually do these patterns, I actually want to use a solid number just so you get an idea of kind of the action here, the pattern. So if I have like something like 5 times f and I want to take the derivative of this. So the idea with coefficients is basically they just follow along. So a coefficient doesn't change how you take the derivative. In fact, basically the coefficient just gets multiplied by whatever the result is for the derivative. So what I'm saying here is whatever the derivative is for f, still what our answer is going to be, you're just going to multiply it by that 5. So you just coefficients multiplied by the function, the coefficient also multiplies by the derivative. Basically, the coefficient just follows along. It doesn't actually affect your derivative. That's the biggest thing that's really, like I said, this is our pattern for derivatives, and that's the biggest, maybe the best way to think about that pattern, or the biggest connection that you need there. That the coefficient doesn't change how you do your derivative. It literally just follows along. So, for instance, if I had something, let's say we had something like, I don't know, let's do 4 times x to the 6, and I want to take the derivative of that. So f of x is 4x to the 6. Then when I go for the derivative on this, 4 is just going to follow along. In fact, it's going to multiply by everything else that's going on. So I'm still going to drop the 6 in front. So I'm just going to end up with 4 times 6x. And what power am I going to have there? So it's just going to be 5. What's 4 times 6? 24. So the derivative there is just 24x. So the coefficient just follows along. Right. With that in mind, there's two other derivatives I want to look at. So like I was saying before, to get at some other patterns with derivatives. The first is going to be the following. So at first time f of x, let's make it 3x. And the second time f of x is just going to be, say, maybe the number 7, something like that. Let's see if we can figure out the derivatives. And what I'm saying is actually you should be able to get the derivatives of these just using the 2 patterns we know so far, the patterns for power functions and the patterns for what happens with coefficients. So this is one actually, so I want you to experiment a little. I want to see, I'm going to give you a chance to see if you can figure out the derivatives here. Then we'll come back and look at what you're getting and also kind of look at what it is. All right, so I'll pause on yours. Well, and one of these you may have had trouble with. In fact, I'm willing to bet the constant is the one you may have had trouble with, and that's actually understandable. This one, maybe you had trouble for a second, but then you kind of figured out the trick there. So notice that, so this is 3 times x. We do have an x, so technically we have a power function there. What is my power? Yeah, and maybe you didn't see that, and if you didn't see that, now you do, and I'm sure, again, it's something you've seen all along through college algebra, pre-calculus. When we have a variable by itself, we can always imagine it as to the first It's like it's to the first power. Now it's a power function. My derivative there, I'm gonna do 1 times 3. But then it's gonna be x to what power? So 1 less than that is 0. So it's gonna be x to the 0 power. But we know what is anything to the 0 power? Just a 1. So this is really just 1 times 3 times 1. This is really just 3. We start out with just an x. The derivative is just your coefficient. It's whatever is in front of x. Now the funner one is number 7 here. F of x equals 7. This one, this is just a constant. So this is why I didn't want to use the word constant earlier. So this is just a constant. However, even this we can imagine as a power function, because remember that x to the 0 is 1. So I could write this in as 7 times x to the 0 if I wanted. I haven't changed anything. 7 times 1 is 7. It is still 7. But now let's use the pattern for power functions. So I'm going to multiply by 0. F prime is going to end up being 0 times x. X to what power? 0 times x to the -1 power. But what is 0 times anything? The big fat 0. Well, we started really with a constant and the derivative was 0. Now I want to go back to these two. So imagine there was on 6, I started you out with still an x, but just some other coefficient there. When I take the derivative, what's my result going to be? What do you think your result's going to be every time? What's the pattern? Every time your result's just going to be a coefficient. So this is, so I would say again, this is not its own pattern. It's really the power function, but it's enough to mention that if I have we'll just say if I have a linear, so I guess we'll title this, that's really a linear function. So the derivative of so now I'll say the coefficient is c. So again, that all I'm saying here is that it's some number. If I take the derivative of this, and all I get is just have the x derivative of coefficient times x, just the coefficient. And last of all, going back to number 7, well, I started with a constant 7. So the question is, do you think it matters what constant I start with? If I take the derivative of a constant, what do you think I'm always going to get? Always going to get 0, because this little play is going to work no matter what that number is. You can always write x to the 0 in, and 0 times anything is 0. So the derivative of a constant is always 0. That's kind of the last one I'll write over here. So the derivative of a constant is just plain 0. These I'd say are your first 4 major patterns for derivatives that are gonna help you do some of the work that we see here. Let's talk about another pattern for derivatives. What we need to do is we definitely need to, so we'll talk about another pattern, but we also just need to talk about some other types of functions for derivatives. And once we have that, then we can start some of the derivatives, some of the exercises from the book. But let's, so the next pattern we maybe want to talk about, let's see, I think I want to, wait a second. Yeah. let me put this pattern over here. So this next pattern. So I'm gonna call this pattern, or we're gonna title this pattern adding, subtracting. So the idea with this pattern is they went and in general, kind of theoretically tried to prove what happens when you got two functions and you add them together and you take the derivative of whatever you get when you add them together. So two functions, let's say f, g, and you're gonna add. So I say you can either add or subtract them, but the pattern's the same. Yeah, and by this point in mathematics, you know that subtraction is just adding a negative. So any pattern that applies to addition applies to subtraction. Um, and so the kicker with this pattern, the thing that you want to remember, like I said, not necessarily want them in, or if you don't have to, you don't actually have to memorize the forms here. And you want to memorize what they're saying. So for instance, with power functions, you can memorize this, but what this is trying to say is the derivative of power function, you multiply by the power and you drop the power by 1. That's really the thing you want to remember in your mind. However you can get that to stick in your mind, that's actually the thing you want to remember. Or coefficients. You could memorize this, but what I'm really trying to say with this is, like I said, the coefficient just follows along. That's the thing you want to memorize. Or a linear function. The derivative of a linear function is just the coefficient. Or a constant, the derivative of a constant, 0. It's like, you want to memorize that. And if the form helps you memorize it, that's great. If the form doesn't, then you just want to memorize that pattern, that sentence, that voice in your head. That's actually the thing you want to remember. So with adding and subtracting, what we're trying to say again is if I have two functions added or subtracted together, what the pattern they found is that, again, kind of like coefficients, adding and subtracting doesn't change how the derivatives, like what the results of the derivatives are. So basically, if you're adding or subtracting two functions, you can take the derivative of the one function and the derivative of the other function and then just stick them together with their plus or minus, whatever that sign is. So the derivative of two functions, either added or subtracted, it doesn't matter. It's just you take the derivative of the first one, the derivative of the second one, and you put plus or minus between them. So adding and subtracting, again, what we're trying to say is adding and subtracting doesn't actually affect derivatives. You can take a derivative of each piece and just stick them together. Look at an example of that. So kind of going off of that we had just that we're doing that we had just done here. What if my function is, let's do 5x cubed minus maybe 4x squared. I want you to take the derivative of this. Now again, this is a polynomial, so you're used to seeing this encoding in your mind as a polynomial, and that's true. But remember, the polynomials are just power functions combined together, added, subtracted. Well, yes, this is a polynomial, but you can also see this is two different functions. This is 5x cubed and negative 4x squared. And so when we take the derivative of this, what we're saying is you can just take the derivative of each piece and then just stick them together with the appropriate addition or subtraction. That's your answer. And that's what this pattern is really saying. So for instance, on the first part, you want to take the derivative of the first part. How would you take what would you do to take the derivative there? Bring the 3 down, multiply the 3 down, so we end up with 3 times 5x, and to what power? That would be squared. And then we could take the derivative of the second part separately. So 2 gets multiplied by the negative 4, so just cut by the 4, so minus 2 times 4, x to what power? First power, but we know we don't then need to write that one. So what we end up with is 15x² minus 8x. That is the derivative of 5x³ minus 4x². I'll give you guys another really quick to do, kind of along those lines. Then some of the other stuff we did. I keep writing f. You could name these functions anything you want, kind of like you've seen in your math classes. So, let's say g is -2 x to the 4th power. Say plus 6 over x to let's say the 3rd power. Now I want you to find the derivative of this. I want you to find g prime of this. So again, you can just do each of these individually and tag your answers together. So go ahead and pause on your side. I'll pause on my side. See if you can work that out. All right. Working this through. So again, we're going to multiply by 4. So I'm going to start writing this things out without all the steps. So multiply by 4, you get -8, and then it's going to be x to what power? Cubed. Then remember that this is really, so this 6 over x cubed, you can rewrite that as 6x to the -3. Then I'm going to multiply by -3. That'll be -18x. And what power is that going to be? But -3 minus 1 is a -4. That's going to be my answer. And you can also write this as -8x cubed minus 18 over x to the 4th. So again, notice literally the powers just go down 1. All right, good. So 2 different functions, or 3 different functions, or 4 different functions, by the way. So this generalizes to any number of functions. We're just trying to say is if you have separate functions separated by addition and subtraction, you can work each individually and just slap them together, and that's your answer. All right. So I would actually say, I mean, so these are one of our main patterns so far that we're going to work with. And actually in the next couple sections, there's only a couple other patterns that we're going to learn. I'm sorry. Well, yeah. So beyond that, what you do need to learn is, so kind of like that first pattern that we learned was about power functions, right? So it was a certain type of function and the pattern for taking the derivatives on there. So sorry, yeah. So we'll have 2 more patterns that kind of have to do with call it operations. But we also need to learn patterns for derivatives with other types of functions. So far everything is, we've basically just sort of made everything into a power function. But not all functions can be made into power functions. So we need the patterns for derivatives with other types of functions. So that's the other things that I want to show you. That I want to put here as patterns. So other types of functions. Let's see. Just see. Gets us square roots. Okay. So other types of functions. So derivatives for, let's look at some trig functions. So the trig functions also notoriously, so there's another reason why, sort of an advantage that you guys get in that you, go ahead, my man, eat as much as you want. The advantage you get is you don't have to spend a ton of time doing mathematical proofs and proving things, for instance, like I said, for um, functions like sine or cosine or tangent. Because one of the interesting things is those actually end up being sort of notoriously hard to deal with, even algebraically. So it's not that the algebra works there, but you actually have to fold in some geometry. Things from geometry, you just have to fold in some pretty advanced algebra technique to get the derivatives. You get the advantage of you don't have to spend all the time it took historically to figure these things out. I just get to write it on a board for you and you just get to use it as a pattern. So let's look at some derivatives with trig functions. So the one I want to start with, let's start with sine, so your classic trig function. And let's say we take the derivative of sine. So the other cool thing about this, besides me just being able to show you a pattern and you being able to use it, is that so you guys probably just came out of a pre-cal class before this, and especially when you were looking at some of the identities for trig functions, you saw some relationships between the trig functions, sort of some patterns or associations between the different trig functions. And you also saw some patterns and associations between sine and cosine going all the way back to the beginning of the pre-cal class because they had you graphing them, and you saw that actually sine and cosine are really the same function, just there's the difference is a horizontal translation, right? So they're different functions to begin with, they're different ratios in terms of a right triangle. But once you visualize them as a function using the unit circle, it ends up that they're actually the same, so the graph of it is the same, difference is just horizontal translation. So that automatically tells you that there's some sort of relationship between those. And graphically, you saw that relationship in the pre-cal class. I think one of the cool things about derivatives and calculus in general is it starts to actually give you some more definition to that connection and that relationship. It shows you more connections between these trig ratios. So for instance, one of the connections is I take the derivative of sine, I actually get cosine. The derivative of sine. So what I'm going to do is I'm going to show you the derivative. So let's say f of x is sine of x. I take the derivative of this. So it ends up that the derivative of sine is cosine. So not only do sine and cosine sort of have relationship you see on the unit circle where their values are off by 90 degrees, and therefore on a graph you see that it's the same function, they're just translated 90 degrees. But it ends up that the slopes of the tangent lines on a sine curve are actually the cosine values at those angles at those points. Then I think the natural question is, well, what's the derivative of cosine? Um, what if I set my function as cosine and I want to take the derivative of that? Well, it ends up if you take the derivative of cosine, slopes on the cosine curve, the slopes of the tangent lines are negative sine of x. The derivative of sine gets you cosine. The derivative of cosine gets you back to sine, but with a negative. And if you think about it, let's say I started with negative sine x and I took the derivative of that. We just saw the coefficients just follow along. So the negative in front is just a coefficient. So The negative is just gonna follow along. And what's the derivative of sine? Cosine. Sine goes to cosine, cosine goes to negative sine goes to negative cosine. And again, part of what's happening here is actually the way a lot of mathematicians work is there's just a natural curiosity. You kind of see a pattern or a trail happening and you're like, okay, let me keep playing this out. Let me see where this goes. So sine goes to cosine. That's awesome. Cosine goes to negative sine. Holy crap. That's actually kind of cool. We sort of get back to sine with a negative. Then that means negative sine will go to negative cosine. So then, yeah, I'm still curious. This is kind of awesome. Where does negative cosine go? Because it seems like there's some, there seems like there's some pretty tight connections and relationships here. Could it get me back? Sine. So let's say, no matter what. So now let's say I set the function as negative cosine, and I take the derivative of that. Well, again, the negative follows. And what's the derivative of cosine? The derivative of cosine is negative sine. So it's going to be a negative sine. That is just plain old sine of x. The derivative of negative cosine is sine of x. So the interesting thing with sine and cosine is that it creates actually kind of a cycle of derivatives. So if you start with sine, the first derivative is cosine. By the way, so we've been doing the derivative of a function. So if you take the derivative, we call that a second derivative, right? So we're now naming how many derivatives down we're taking. We'll kind of see that in some of our work. We're gonna have to start doing some second derivatives in this chapter. But a second derivative is just a derivative of a derivative. A third derivative would be the derivative of the second derivative, right? So what we're trying to say is any function you see, you can take a derivative of, right? So the first derivative of sine is cosine. And then the second derivative from cosine, the derivative of cosine, second derivative would take us to negative sine. The derivative would take us to negative cosine, and the fourth derivative finally takes us back around to sine. Or again, we could just say the derivative of sine is cosine, the derivative of cosine is negative sine becomes negative cosine, and negative cosine takes us all the way back around to sine. So with power functions, we saw that when you took the derivative, it changed the power, right? The power went down and it changed the coefficient. So you're really getting sort of a different answer. And if you kept taking derivatives, it would keep changing the answer. But with sine and cosine, what we're seeing is that there's a cycle of answers. So back to the way I like to show it. If I'm taking derivatives here, the sine goes to cosine. So the derivative of cosine. The derivative of sine is negative, or cosine, sorry, it's negative sine. All derivatives. And then the derivative of negative sine is negative cosine. And the derivative of negative cosine finally takes us back to sine. So you get a cycle of derivatives between sine and cosine. This is another pretty awesome pattern we'll take advantage of or use. All right. Right, so that covers sine and cosine. Let me just give you the summary on a couple other trig functions. much all the other trig functions. So, um, well, another interesting connection that you guys saw in, um, another interesting connection that you guys saw in pre-cal was the connection sort of between tangent and secant that came through the Pythagorean theorem. That tangent squared was kind of connected to secant squared. And the same with cotangent squared was connected to cosecant squared using one of the versions of the Pythagorean identities. So the interesting thing is that you see further connections between tangent and secant, cotangent and cosecant. You take derivatives. The derivative of tangent ends up being secant squared. What next there? If you take the derivative of tangent, you get secant squared. And in a similar way, and algebraically for similar reason, when you take the cotangent, the derivative of cotangent, get negative cosecant squared. Then the other trig ratios that we have, what are secant and cosecant. Take the derivative of secant, get secant x tangent x. Take the derivative of cosecant, get negative cosecant x cotangent x. Tangent and cotangent, your derivatives end up being squareds. So tangent is connected to secant, so secant squared. Cotangent is connected to cosecant, negative cosecant squared. Then the interesting thing is for secant, at least the interesting thing to me, secant and cosecant, when you take the derivatives, basically get the same function back, but multiplied by the other trig function that it's connected to. So you basically get an expanded version of the original. You get the original, not really plus an extra piece, but times an extra piece. And that's an interesting behavior, I think. So again, with power functions, you take derivative of power function, you get a different power function, right? But then with sine and cosine, you get this sort of circular cyclical behavior. Secant and cosecant, you get this behavior where the derivative is itself times something else. So it extends the original. You can imagine what happens then if you take the derivative of secant x tan x. We'll actually get to that in another lecture, another section. Let's see. What we have left in terms of types of functions. So if you think of types of functions that you've dealt with both in total in algebra and pre-calculus. So again, you dealt with power functions and polynomials, but polynomials are just power functions added together. You dealt with rational functions, which we'll do more of them in another couple lectures, but some of them are just power functions like we saw. You dealt with radical functions, but you also dealt with trig functions. This is how we'll deal with trig functions with derivatives. The other two types of functions that you dealt with were exponential functions and log functions. So let's summarize those. Exponential functions. And when we do exponential and log functions, we're going to use base E. And something that I'm not going to go through showing that show in a class like this, that all exponential and log functions, you basically can also for reasons that come about because of the derivative, the natural number ends up being sort of like the central base that you can relate them all to. So we're going to use the natural number for these. So if I want to take the derivative of e to the x, so exponential function. Wait, let's just exponential and log. I want to take the derivative of e to the x. So talking about interesting patterns with these derivatives, just kind of interesting happenings. So like I said, we have one set of derivatives that are cyclical. This weird set here where it sort of adds something if you take a derivative. With e to the x, the interesting thing is that this is the only function we know of. Only function ever that when you take the derivative, it doesn't change anything. The derivative of e to the x is e to the x. Which means again, if you think of the e to the x graph, what I'm saying is slope of the tangent line at every point on the e to the x curve is e to whatever that x is. The slope matches the actual y value at the point, which it is the only function we have that does that. The derivative of e to the x is just e to the x. And log base e is natural log. And the derivative of natural log is actually 1 over x. This is another set of patterns to work with. And once we have that, we've actually covered most of the functions that you guys have seen up until this point in mathematics. Power functions, basically the same power functions, patterns for sine and cosine, basic patterns for your trig functions, an exponential log. That'll actually cover not everything, but that covers most of the things we're gonna see and most of the functions you've seen so far in mathematics. And this will cover enough patterns for us to do kind of the work today. So I mean, we've already to do. I'll start picking some exercises out of the book and we can work those. In the next two sections, you'll look at one pattern each, one new pattern each, for how to find derivatives. Once we're done with that, surprisingly, I think there might be in the later chapter, I think in one place there's another couple, I wouldn't say patterns, but new patterns, but just a different strategy you need to approach a couple of the derivatives. But other than that, so again, once we're done with the next two sections, you've actually seen all the patterns that you need to for derivatives. That'll get you everything you need. So, so right now, kind of take this, take a picture of it or whatever, just kind of commit these patterns to memory. Let's use them. Use them on your homework. I'm saying like this is actually commit these patterns to memory. I'm not saying memorize them. I'm just saying find a way to take every one of these patterns and what they mean and just basically know how to work with it, know what that is and how to work with it. Because this is going to be it. This is going to get us everything we need. So let's exercises out of the book. By the way, these exercises I'm giving you, some of these are exercises that would also be in the book. So just again, know that there's nothing special about the exercises in the book. I can make up all my own exercises and you could do them and you'd be able to do everything in the book. But also for just the convenience of those things already being written there, let's start working some of them in the book. Do a couple problems out of the first section. So this is 3.1. These first couple problems they want you to find, or this first problem that I do want you to find the derivative. And this one at 3.1. This one, this is 21. And the function here is x squared plus x minus 3, and I want you to find the derivative. So go ahead, this is a quick one, but pause on your side, pause on my side. Go ahead and find that derivative. Alright, so finding the derivative, easy here again. So this is just a bunch of power functions, so derivative is gonna be 2x. And then the coefficient here is 1, so that's just plus 1, and then the derivative of a constant is 0. So this is just gonna be 2x plus 1. You've got it. Like I said, your problems are either gonna ask you to find a derivative, or you're also gonna see these problems where they want you to find the actual slope of the tangent line. So let's do something. That you guys can see it. Pull ones first, we'll just kind of keep building up. So this is 13 again on section 3 points. Three t minus t squared. And the points on the original function that they want us on the slope for is 0, 0. Oh, sorry. So this is f of t. That when you plug in 0 to this, you get 0, so that's where they're getting. So they're saying, so basically an x value of 0, what is going to be the slope of the function? You're going to remember the slope is just the derivative. So you're going to find the derivative, just plug in your 0, and that'll tell you the slope. You guys can easily do that. So go ahead and pause on your side. I'll pause on my side, and I'll have you do it. All right. So first of all, what did y'all get for the derivative here? So f prime of t, what is that going to be? This one, so you should get 3. That down, so it should be 3 minus 2t. So then my slope, f prime of 0, is going to be 3 minus 2 times 0, which is just a 3. So my slope is f prime at 0. So my slope is 3. The slope of the tangent line is 3. Good. And then you're going to get a third variety of problem. So find the derivative, just do the abstract thing. Again, so you get a function that is essentially a catalog of all your slope values. Find the slope where you plug in a specific x value, get your actual slope on that tangent line. Then taking you guys back to Be back to early. Public algebra classes. They're gonna have some problems where they want you to find the equation of the tangent line. Now, just thinking back to our picture earlier, a tangent line is a straight line, right? So to find the equation of a straight line, so again, go back to your early college algebra days, to find the equation of a straight line, what do you need? You need a slope. You need a point that it goes through. At least that's one of the ways of finding the equation of a straight line. You also gotta have slope and y-intercept, but you'll see with this, there's just contexts of these problems, never really know the y-intercept. But as long as you know the slope and one of the points that it goes through, we can use the point slope form to write the equation of the line. So that's what you're doing here. So again, you know, this problem, even if I didn't teach you how to do this and you'd never seen it, you're just, all you ever got to do is just think through the tools that the things you do know and the tools that you do have, and just kind of identify what you need. So to find the equation of a line, you need a slope and a point. So out of the information they give me in this problem, I just got to be able to get the slope of that tangent line, which we already know how to do. That's the derivative at that particular x value. And we need the points, which they usually give us. So they gave it to us on the last problem. There you go. We can use that to make the equation of our straight line. So let's kind of work that through on another problem. This time let's start branching out a little bit on our functions. So this is 35. By the way, so okay, this is 13. That's what I forgot to rewrite. This is 35. And all in section 3.1 right now. So the function here, f of x. X plus 4 over x. Points. -4, -5. Indeed, if you plug -4 into this, you'll get -5. So we need to find the equation of the tangent line. The slope of that tangent line. Once we have that, we have this point that it goes through. So we should be able to use that to find our equation. First thing is we need the slope of the tangent line. So you basically need to do all of this first, solve this problem. So let's go ahead and do that. Pause on your side, I'll pause on my side. Let's see what you get for the slope. All right, let's see what y'all got. So first we need to figure out the derivative. And the derivative here is going to be 1 plus, and remember, so this is, think of this as 4x to the -1. Take the derivative, the negative is good. 1 is going to multiply, so it's really going to be -4. And then it's going to be x to the -2, so I'm going to write that as 4 over x squared. So over x squared. So then I want the slope. So slope be f prime at -4, so we need to plug that in. So that's going to be 1 minus 4 or -4 squared. -4 squared is 16. 4/16 is just 1/4. So this is 3/4 over. My slope is 3/4. And if they ask me to find the slope, I'm done. Beautiful. Dust your hands off. You got the answer. They're asking me for the equation of the tangent line. So for here, you have to remember You can kind of remember this honestly one of two ways, but pretty much you want to remember the point slope form for the equation of a line. So the point slope form says y minus y1 equals m times x minus x1. By the way, this form comes from the formula for slope. So really quick, you think about the formula for slope, we said it was delta y over delta x. So the delta y, kind of like we did for finding that derivative, is y minus y1. That gives you the difference in your y values. X minus x1 gives you the difference in your x values. So literally this equation, if you just multiply both sides by x minus x1, get this. So that point slope form that you guys were taught, it really just comes from the slope formula. So you technically don't need the point slope form, you just need the slope form. But it is really, I'd say honestly, algebraically, it's really nice, just for the work you're gonna do, it's really nice to memorize it this way. Because it comes, the algebra is pretty clean from here. All right, anyways, so, but they call it the point slope form to suggest kind of what to do here. You need to plug in your slope, you need to plug in the x and y values from your point, and once you've got that, we're just gonna basically get y by itself. We're gonna work out the algebra really quickly from there. So point they gave me, the y value is -5, so that's y minus a -5, so y plus 5. M is 3/4, my slope is 3/4. And I'll have x minus a -4, so x plus 4. That means, so we have parentheses we can distribute there. So y plus 5 equals 3/4 x. 3/4 times 4, think of this as 4 over 1. Well, I want to write it there, but think of it as 4 over 1. Multiply the 4's cancel, and so you end up with just 3 over 1 or 3. And then I'll subtract 5. So my equation for that tangent line is y equals 3/4 x minus 2. And I'm good. I got my equation. So hopefully this took you down a good memory lane back to, like I said, some early algebra classes for you. But also hopefully it took you down that memory, that a good early memory lane. This is easy algebra from here. All right. And so actually all the problems in these first two sections are either find the derivative, find the slope of the tangent line, or find the equation of the tangent line. And you see they kind of literally build on each other. So let's do some more like that. Let's do a couple more like that. Let's do some problems out of 3. Find a derivative.
You go to the bathroom.
Go ahead, my man. Go ahead. Get something. This is 24 out of 3.2, so out of a different section. So 24. And my function is 7x to the 4th plus 2 sine x. And they're asking you to take the derivative of that. So I gave you guys patterns for trig ratios, so you should be able to handle that as well. So same thing as usual. Go ahead and pause on your side. I'll pause on my side. Let me actually move the camera so you guys can see that. Pause on your side. run through that and then we'll come back to. And we are back. So easy enough, the 7x to the fourth. That's using the power rule pattern, so 4 gets multiplied by the 7. This is gonna be 28x to what power? That'll be 3. And on the second part, so again, the coefficient's just gonna carry with it. And what is the derivative of sine x? That's cosine x. And you've got it. Oh yeah, there's a couple different other types of things. For the sake of, honestly just doing some derivatives, let's do a couple more. Couple more of these derivatives before we move off onto the other problems. So I'll have you guys do, so 26. So 3/4 EVX plus 2 cosine of x. So our, for whatever this is, of x is this. But we want to find the derivative. And I think also. We'll look at 54. It needs some room here, so let me erase this. For now. When some of these problems, instead of writing f of x, they're writing y. Yeah, like you've talked about forever in mathematics, you know that f of x means y. But I just want to kind of point that out. When they do that, it doesn't change anything. It's just, again, it's like writing in a different language, just different symbol. But then, so then the derivative, they'll write it as y prime instead of f of x prime. But same deal, so we want to find the derivative of that as well. So I actually want to give you time to work both of these. So go ahead and pause on your side, I'll pause on my side, work both of these, and we'll come back and make sure you're getting the right thing. Let's see what you guys are getting. So going to 26. One thing with this one, again, the derivative of e to the x is e to the x. And the coefficient just comes along with it. That drops down as well. So actually the derivative 3/4 e to the x is just 3/4 e to the x. And the 2 stays as well. So the only thing that really changes on this one is the cosine. The derivative of cosine, sorry, that is the wrong sign there. The derivative of cosine is negative sine. So this is then minus 2 sine x. That is our derivative. So the one with really a little more work here is 54. We have a cube root here, and so again, we have to do what we've seen several times so far. So again, you're going to keep seeing it as you go throughout this class. In order to do work with basically radicals and fractions, when you can, you need to retranslate them into exponents because the pattern for power functions then applies. It's much easier than some other way of dealing with it. Also, I would add not just for the sake of these type of functions, but you're going to keep seeing that throughout Cal 1 and Cal 2. It is a huge skill to turn these into their exponential form, because that's how we're going to get a lot of the work done. So really quick, in exponential form, this would read, so that's cube root is a 1/3 power, so this is x to the 1/3, and it's on the bottom. So this is gonna be 2x negative 1/3 plus 3 cosine of x. Now I want to take the derivative. Now I'm gonna multiply negative 1/3 by 2. It's gonna be negative 2/3. And then it's gonna be x, but my power is gonna be negative 1/3 minus 1. So what is negative 1/3 minus 1? That it's negative 1 1/3, but in as a fraction, that is negative 4/3. Talk about how to rewrite that because that's actually also really important. But still, like that's correct. That's it. And what's the derivative of cosine again? Derivative of cosine is negative sine. This is going to be minus 3 sine of x. So is this correct? But again, as a point of talking about how to rewrite this. So we're going to have negative 2 on top, 3 on bottom of the fraction. Negative on the exponent tells me this is on the bottom of the fraction. Really quick, I want to talk about, so I mean, we've been rewriting something like x to the 1/3 as the cube root or x to the 1/2 as the square root, but how in the world do I rewrite something like 1/3's power? The denominator still means your root. So what this is saying is this is the cube root of x but then the top is your power. This is gonna be -2/3 cube roots of either, so you can write x and then a fourth power outside, or you can write the fourth power inside. Because of the patterns with exponents, it reads the same either way. I think to be consistent with not only the way we're gonna see it in problems in this class, but I think the work we're gonna have to do in this class, derivatives, I'm gonna write it outside, I think it helps. So -2/3 cube root of x to the fourth power. -3 sine of x. And that is another way you can write it. Some skills that'll help us as we go along in this class. Good. All right, good. So this is gonna be another day where, so you guys don't sort of realize it on your side, but it's actually pretty late here. We still got some more to finish here, but I think what I probably won't do a find the slope of the tangent line and find the equation of the tangent line problem, just because I need to wrap this up quick. So again, on y'all's side, I don't know where we are in the video, but on my side, um, I've been working on this video since 5:30 and it's 9 o'clock, so I need to get done with this a little quicker. Let's see. Um, so, but I'm also, if I really felt like you guys needed more work or more practice on this, find the slope of the tangent line and find the equation of the tangent line, I would do it anyways. But you guys got the idea from there. Not only from the problems we've done, but you've had enough algebra in class. You know, you've seen problems like this in algebra classes before this. You know how to plug in a number and you know get a slope, get a number, or get a y value out of it, and you know how to um, use your point slope formula and get an equation of your line. So I'm gonna leave you guys to do those problems. Um, just knowing that you guys have the algebra skills for it. I want you to know that you have the algebra skills for it too. So again, I'm not just trying to get out of here less than 4 hours. But you guys really do have the algebra skills. You don't need to practice it maybe as much as you might be worrying about. What I want to do then is I do want to look at a couple more find the derivative problems. There's gonna be some functions that on first look they're gonna be like, you're gonna be like, wait, hold on, what's going on? This often happens in mathematics. So you run through sort of let's say the regular bevy of problems, the easy problems, the medium problems, and then the harder problems are, I don't know, your experience may be different, but what I've seen, the harder problems are not really usually that much harder, or really sometimes any harder at all. What they do is they write it in a way where they're trying to see if they can fake you out. They're trying to see if they can get you to be like, oh my goodness, that looks different and I don't know what to do with that. So shit, I can't do this problem. They're just trying to fake you out. So let's look at some problems where they're trying to fake you out, um, and just work our way through the derivatives. Oh yeah, and there's one other type of problem, so that we have to look. Ah, too many types of problems. So, well, let's look at something like 46. 4x cubed plus 2x plus 5. They put this all over x. You get something that looks like this. They're going to ask you to find the derivative. Now again, so they're trying to fake you out. So this looks weird and possibly horrible too. You have gigantor fraction, you have big bit up top, you have this one term at the bottom. And that looks like a lot to deal with. And it just looks very different from anything that we've seen. Everything we've seen so far has been sort of separate, separate or functions separated by plus. So we've had one thing plus or minus another thing plus or minus another thing, etc. And this one suddenly throws in this big fraction bar divided by x. So again, but what they're trying to do is fake you out, because if you remember, dealing with a fraction like this, as long as you have one term on the bottom. So this only works if you have one, well, roughly, I'll say basically this only works if you have one term on the bottom of the fraction. If you have one term on the bottom of the fraction, we can break this up into several fractions. So what I'm saying here is, remember that what you see there is the same as 4x cubed over x plus 2x over x plus 5 over x. Because remember, this is how fractions work when you're adding and subtracting. When you're adding and subtracting fractions, you have, and as long as the denominators match, you can add everything up top and then just slap the denominator on the bottom, right? So 6/5, 8/5 plus 9/5, right, is 6 plus 8 plus 9, which is 23/5. So we're using that same factor, that same idea, we're just using it in reverse. So instead of combining several fractions into one piece, we're just pulling them back apart. So think about it like an accordion. Washing it together, you're pulling it back apart. So I'm just pulling this back apart into its separate fractions. And notice that this is helpful. So I agree with you. So if you look at this and you're like, that's crazy and that's weird and I don't know what to do with that, I agree with you that this form, we can't do anything with it because it isn't separate pieces. But now look, it is separate pieces. In fact, it's separate pieces where we can actually simplify what we're looking at, like the 4x cubed over x, one of the x's cancels. So what does that simplify to? That's 4x squared. What does 2x over x simplify to? That's a 2. And now the 5 over x doesn't simplify. Okay. So okay, because I can rewrite that as a power function and go from there. So in truth, we can do this derivative as separate pieces using the power function pattern, but we can do this derivative like any of the other ones in these two sections. So let's go ahead and do it. Pause on your side, I'll pause on my side. Let's see where you guys got on this. Let's see, so h prime then. I'll just kind of note this is 5x to the negative 1, so h prime is 8x, and 2, the derivative of 2 is 0. And this one then would be minus 5 over x squared. And that would be my derivative. Let's do one more sort of like kind of like that. And I don't know if you guys could even. So let's look at something like 47. Three t squared plus 4t is 8 divided by t to the 3/2 power. So notice same thing, really same setup, one term on the bottom. So we're just gonna split this into 3 terms to begin with. 3t squared over t to the 3/2 plus 4t over t to the 3/2 minus 8 over t to the 3/2. And then the kicker with this one is just simplifying these. So I would say trying to fake you out here is not only the way it looks to begin with, but even if you get here, they're trying to fake you out with the 3/2. Trying to make you think that you're gonna need to do something different, and you don't at all. So like on the last one, you could kind of see the x's cancel. Here you kind of can't see the t's cancel, but you still just do the same pattern with your exponents. You subtract your exponents. You're dividing with exponents, so you subtract with your exponents. This one is 2 minus 3/2, or 2 minus 1.5. And what does that leave you? Good. So 2 minus 1.5 is going to leave you 1/2. So this is going to be 3t to the 1/2. And then here, this is t to the first power, so 1 minus 1.5. What is that going to leave you? That's going to leave you t to the negative 1/2. Or you could imagine it as t to the 1/2 on the bottom of the fraction. And again, on the end, that there's nothing I can simplify there, but I will just rewrite it as a negative exponent. Again, just basically just don't let the fractions throw you off. You even now doing the derivative, you're going to do the same thing you've been doing. So again, you guys pause on your side, I'll pause on my side. Go ahead and work the derivative out there. Right. So 1/2 times 3 gives you 3/2, and then you're going to subtract. So this is going to be 1/2 minus 1, which is negative 1/2. So 3/2 t to the negative 1/2 power. And then you're going to do negative 1/2 times 4. That is negative 2. And you're going to do negative 1/2 minus 1 on the power here. That's negative 1/2 or negative 3/2. So t to the negative 3/2. Just as a small note, it's not that the mixed number is correct, but it's not simplest form, basically. So simplest form is writing as a fraction. So I will say on that, in Canvas, if you wrote t to the negative 1.5 power, they would count it wrong. And you have to know it's not because it's wrong, but it's because it's not in simplest form. So a mixed number is literally a whole number mixed with a fraction. So it is in no way the simplest way that you could write that. So just basically if you aren't already, just kind of get comfortable writing the actual fractions there. And then with this last one, we have negative 3/2 times 8, negative 8, sorry. So that's going to be plus 8 divided by 2 is 4, 4 times 3 is 12, so plus 12 e, and then negative 3/2 or negative 1.5 minus 1 is negative 2.5, which is negative 5/2. So t to the negative 5/2 power. That is your answer. And again, if you want, you could rewrite this, both rewriting the negative powers, but then also rewriting fractions as roots. So what you'd end up with there, it's going to be, the first one's going to be 3 over, so this is a negative 1/2, so the t is going to be on the bottom, and 1/2 means square root. So this is going to be 2 times the square root of t. On the second one, we have 2 on the top. Then on the bottom, we're going to have the square root of t. So like we were talking about with that previous problem, the denominator here means square root. U means my power. So this is going to be the square root of t power. And on the last one, it's gonna be plus 12 over, that is gonna be again the square root of t 2, but now it's to the 5th power. So that's another way we could write that answer. All right. So now, let's see, let's go back to 54. Let's look at one last type of problem that you'll see out of these, really out of the second section out of 3.32. But also it's actually a type of problem. Not only are you gonna keep seeing it in sections going forward, but the idea behind it is gonna be really important actually next chapter. So let's take a look. One more. All right, so we're gonna look at number 63. Number 63 has a different set of instructions. So they're gonna say, find the points on the graph. So find the points on the graph. If, yeah. It's 46 here. With a horizontal tangent line. In some ways, also, honestly, this kind of fits into the end of this lecture where I'm talking about problems that it fakes you out. I think probably the instructions on this would fake you out. Because it's just mentioning things. It's like, how do we get from find the derivative, find the slope of the tangent line, find the equation of the tangent line to find points on the graph with a horizontal tangent. It's like there seems to be a bit of a conceptual or just a bit of a contextual jump there, right? Again, when you get problems like this, I'll not only just for this section, but you'll see as we go through the course, and I can swear to you guys that, again, if I didn't teach you how to do this problem, you could do it. All you got to do is think through what they're asking and basically what it means and what it intones, because what it means and what it intones will actually tell you how to get through the problem. So there's so many problems in a math class, a science and engineering class that, again, because I've done both. I got a PhD in math, but I also was a material science and engineering major. I've done applied physics research problems, and I promise you, for all that work, for a lot of that higher end work, I would read something. It's like I would read something or figure out what I needed to do in the moment. And there was nobody there to teach me, okay, this is what you do with this. I had to read it, decipher what it meant and what it asked for in the situation, and then use the math and the tools that I have to go find those things that I needed. And so what I'm saying is, I promise you, you can actually do that. Like with your ability and your knowledge level, you can do that. You actually don't need somebody to teach you how to do that. But not only that, you will have to do that. So you'll have to do that in some problems later in this class. You'll have to do that in a physics or a chemistry class, a biology class. You're going to have to do that in an engineering class. You're going to have to do that in research you're going to do for those classes. And then when you finally get to the job, you're going to have to do that in your job. And the awesome thing is you can. So this is, we call it critical thinking, we call it problem solving. All it is though, is it's taking what you know, taking what the situation is asking for and figuring out first, again, this sounds crazy, there's a bunch of coded words there, but figure out what that is code for, what you really need, and then connect that to what you already know so you can use the tool you have to find the thing you need, and then put the problem together from there. So they want us to find the points on the graph with the horizontal tangent line. So the key here is they're talking about horizontal tangent line. Make sure it's not sort of. So first of all, you're finding something about a tangent line. So that means you're going to need a derivative. They specifically want a tangent line that's horizontal. So you have to think back to probably a geometry class or just, what do you call it? Or algebra class that you've been through. So a horizontal line, what slope does it have? Because again, tangent lines are about are about derivatives, but derivatives are slopes of tangent lines. So the way when I read this, I read tangent line and I think derivative. This is kind of how you would get through a problem like this if nobody taught you how to do it. You read tangent line, you're like, oh, that's the derivative. Derivative is the slope of the tangent line. So then the next thing is horizontal. So then, like literally, you can just make the guess of, well, something about horizontal has to have to do with the slope of the tangent line. So what is a horizontal line? What's the slope of a horizontal line? The slope of a horizontal line is 0. So literally, they write all this, but what this essentially says is we're looking for tangent lines whose slope is 0. We're looking for where the derivative is 0. So notice that kind of tells us how to get through the problem. So I don't even know what function it is yet, but I know that I'm going to take a derivative, and then I need to find when is that derivative 0. I'm going to see what those points are. But I need to find a derivative, and I'm going to see when that derivative is 0. So let's look at what the function is. So that my function is x to the 4th minus 2x squared plus 3. Again, I know that I'm looking for derivative. I need the slopes of the tangent line, and specifically I'm looking for when is that slope 0. So I need to take the derivative first. So this is a very quick pause. In fact, I won't even pause. I'll just pace back and forth for a minute. But go ahead and figure out the derivative on this really quick. So what are you guys getting for the derivative here? The x to the 4th, the 4 is going to come down, so that's going to be 4x cubed. Then on the minus 2x squared, 2 times -2 gives you -4, and then the power goes down to 1. Derivative of 3 is 0, so my derivative is 4x cubed minus 4x. And then I want to know, when is my derivative 0? When is my slope 0? So when is my derivative 0? So then all I got to do is set this equal to 0. Then I go solve. Now here I started with a polynomial as a function. When you took the derivative, you got another polynomial. So the nice thing here is I got to solve a polynomial, which in the scale of things is not as hard as maybe some other equations to solve. Depending on what function you get to begin with, though, your derivative is not necessarily going to be a polynomial. So one thing about a problem like this is you are on the hook for solving sort of all the types of equations you've seen before this, right? So could have a trig ratio there, could have an exponential function there, could have a log function. But don't let that again scare you or freak you out. It's just like you're a professional. You've been doing math, you've worked your way through these classes. You do know how to solve all these types of equations. You can solve an equation with a trig ratio, you can solve an equation with an exponential, a log, you can solve all these equations. But like I said, here, or at least it's at least decently nice because it's just a polynomial. So let's solve this polynomial. What x values are going to make the derivative the slope 0? So go ahead and pause on your side. I'll pause on my side and solve that. see what you got here. So solving this, there's obviously a common factor there, so you can factor out a 4x, which leaves you with x squared minus 1. X squared minus 1 further factor into x plus 1, x minus 1. And we can set those all equal to 0 and solve. So we get three solutions out of this. Out of here, so you set 4x equals 0, you get x equals 0. So let's just use arrows here. So this is going to tell me that x equals 0. This will tell me that x equals -1. This will tell me that x equals +1. We actually have three possible x values here and therefore three possible points. Now, a lot of times when we solve equations, we get the x values and we're done. And so, and that's right. They ask us to solve the equation. Find the value for their variable. The one thing about these problems is notice that they want you to find the points. So it's not that this is correct, but we're still missing something with these solutions. So like these are correct solutions, but they're the x values, they're not the, you also need the y values. So to give the point on the original curve or function, I need the y value along with it. So if I know the x values, then how would I go ahead and find the y values from there for each of them? Good. You just plug each of them into our original function. Get the y values. So again, stuff that you guys already know. So this is easy peasy college algebra. I say that not to make light of it. I mean, it really is. It's easy peasy college algebra. This is just stuff that you've been doing in your sleep for a while now. You know how to do this. All right, so x equals 0, f of 0 equals 0 to the 4th minus 2 times 0 squared plus 3, which just equals 3. So my first point is 0, 3. At that point on the graph, if you graph this out, you would find that your tangent line has a slope of 0. So that's one of them. Second one, x equals -1. So f of -1. That is -1 to the 4th power minus 2 times -1 to the squared plus 3, which is 1 minus 2 times 1 plus 3. 1, that's 1 minus 2. Sorry guys, I know I don't have to write all this out for you guys, but just good and bad habits as a teacher. I want to be complete here. So 1 minus 2 plus 3 equal to 2. So my second point is -1, 2. So it also has a horizontal. So again, and I've been using the word or just talking about the word, but just think about the visual on it. A horizontal comes from the word horizon. So horizontal is a flat line. So there would be a flat tangent line at 0, 3, and also a flat tangent line at -1, 2. Also a flat tangent line at, let's plug in +1, which I think ends up being the same here. Some symmetry to this function when you graph it. Maybe at least symmetry in the derivative. But you plug in a 1, so f of 1 equals 1 to the 4th power minus 2 to 1 squared plus 3, which in this case is also 1 minus 2 plus 3, which is also 2. So my third point is 1, 2. Those are my 3 points where the horizontal, where you have a horizontal tangent line, you have a flat tangent line. All right, and that covers not only all the types of problems in this these two sections, so this is sections 3.1 and 3.2, but also all the patterns you're going to need not only to handle these problems, but really going forward. So trust your algebra skills, trust what you know in math, rock and roll with these. I'll see you guys.